We're now ready to describe each of one of the blocks that build an image compression algorithm, and in particular JPEG. And as we say, we are going to start with a symbol encoder. After we have basically done everything, we have done the transform and the quantization that we're going to explain in detail, we want to further compress. So quantization will provide us some compression, but we want to further compress. But we need to save whatever we have produced here. We need to save with no error, but we're still going to see how we can compress. So why can we achieve that? The basic idea is very simple. And of course, you cannot teach image processing without showing at first, at least once, this famous image that is called Lina. That it used to be used a lot in image processing, but now, because of the abundance of images, many other images are used, but I want to show it at least once during these 9 weeks. And we might see the same image again a few more times. So the basic idea is that some pixels, some gray values in the image appear more than others. And let's see that. Here on the right, we have what's called the histogram. The histogram basically counts how many times a particular gray value appears in the image. For example, the pixel value, the pixel with gray values, let's say around 47, appears this amount of times. So we go around the image, we count how many times I see the number 47, and this is the amount of times. Then I can go and see, for example, 200, and I see this amount of time, about 700 times appears in the image. So we see that there are some pixels that appear a lot. There are some pixels, let's say 0 or 1, don't appear at all. And the basic idea that we are going to exploit is that we are going to try to give to pixel values that appear a lot, very short codes, and to pixel values that don't appear so much, we're going to try to give very long codes or longer codes. Let's see how we do that. Let's see an example of the use of this. So here we have an image, and this is actually the image that we saw in the previous video, the geometric image. This is a particular image that there's only 4 different gray values in that image. And they appear, so the pixels with gray value 87 appear in 1/4 on the image. So 25% or probability of 0.25. And we also have 128 appearing almost half of the time in the image. And we also have 186 and 255 appears very, very few times. Everybody else just doesn't appear in the image at all. So the standard way to represent this image is we have an array, and for every pixel, we have a binary code with 8 bits. So we are going to basically represent 87 with its binary representation. We're going to represent 128, which is its own binary representation, and so on. So at the end, we are basically spending 8 bits per pixel if we don't compress. But let's assume that somehow I manage to basically construct a code that is shown here in a way that 87 is represented by the binary code 01, 128 is represented by the binary code 1, 186 by the binary code 000, and 255 by the binary code 001. That means that, for example, if I wanna store or send the pixels 87, 87, 255, 128, instead of writing all these, then this again for 255 this and for 128 this, which will take me basically 4 times 8, 32 bits, I'm going to write it in the following way. I'm going to say, okay, 87 is 01, 87 again, 01, 255, 001, 128, 1. So it basically took me 2, 4, 7, 8 bits instead of 32 to represent the same string, the same form of gray values. Now the decoder has this table. So the decoder will see 01, will go into that pixel position and will put an 87. We'll see 01, we'll put again an 87. We'll see 001, we'll say, oh, I need to put a 255, and so on. And so we have achieved compression. Let's see exactly how much compression we can achieve. So basically, we do a very simple computation. We say, okay, with probability 0.25, I'm going to have length of 0.1, length of 2. That's my code, 0.1. With probability 0.47, I'm going to have length of 1 plus 0.47 times 1. With probability 0.25, so for 1/4 of the image, I'm going to have length 3. And with very small probability, I'm also going to have length 3. And this is equal to 1.81. Okay? So instead of 8 bits per pixel, I'm going to have 1.81 on average on my whole image. And basically, I have saved a lot of pixels. Okay, I have gone from 8 to basically 1.81. And that's a compression of over 4 times. And that's what we have done. Basically what we did is we exploited the fact that some of the pixel values appear more often than others. And then I have to give shorter codes. I can give shorter codes. So how we do that? We do that using something which is called Huffman coding. And I'm going to explain next how to do it. So let's just look once again at this particular example. The best way to explain Huffman coding is just to use an example, and I'm going to do that next. So let's assume that we have 6 different symbols, sorry. And I order them. The first thing I have to do is order them according to the probability. The highest probability first and the lowest probability at the end. And if some probabilities are equal, it doesn't matter which one we put first. So for example, this symbol A2 might be the pixel value 100. The symbol A6 might be the pixel value 77, and so on. So I'm going to add, basically I'm going to list the symbols here and the probabilities here. And from the bottom, I start to add. I take the 2 lowest, and basically I add their probabilities. So I go from 0.04 plus 0.06, and that's probability 0.1. And then I do the list again. So none of these has changed. The only one that changed is the last one. See what's happening here. What's happening here is with probability 0.4, I can get A2. With probability 0.3, I can get A6. With probability 0.1, I can get A1. With probability 0.1, I can get symbol A4. And with probability 0.1, I can get either A3 or A5. I'm going to have to do something to distinguish which one. Is it A3 or A5? And that's going to come in the next slide, how we distinguish them. Now we do this again. We take the 2 lowest, and then we add them. And now, because it became 0.2, remember, we have to reorder all the time. So let me just describe that again. With 0.4, we can get A2. With 0.3, we can get A6. Now, with 0.2, we can get either one of these two, which is A4, A3, or A5. I don't know which one, but I know that with 0.2 probability is one of them. And then we have 0.1 again. We do that once more, actually 2 more times. We add the 2 lowest, we get this. And then we once again add the 2 lowest, and we get this. And once again, every time we add the 2 lowest and we move into the next column, we reorder everything. When we end up with only 2, we stop. And we're going to see why we stop. Now it's time to give the code. So basically what I have done here, I basically redrew the graph that we have in the previous slide. And so this is the first column, this is the second column, and the third column, the fourth column, and the fifth column. And now I'm going to go backwards, assigning codes. So basically to 0.6 I assign 0, and to 0.4 I assign 1. Before we go backwards, let me tell you what's happening. When the decoder is going to see a 0, it's going to know that it's from the group that led to this 0.6. When it sees a 1, it's going to know that it's from the group that led to this 0.4. Then we're going to have to keep adding bits to say which one in that group. And that's why we keep going backwards. So we basically propagate back the 0, and we actually, the 0.6 came from 0.3 plus 0.3. So we add a 0 and a 1. So now, and we of course propagate the 0.4 here, and basically assign it to this that came to this column without adding any numbers. So it keeps propagating without adding any bits. So now all the symbols that led to this group, and we're going to see it was actually only one symbol, will have this code, and all the symbols that propagated to this probability will have symbols that start, we have codes that start from 0, 1. So now we keep propagating. We propagate the 1 to the 1, the 0, 0 to the 0, 0. 0, 1, we have to split because this 0.3 probability came from the addition of these two. And then we have a 0, 1, 0, 0, 1, 1. And then we keep going. We propagate the 1 to the 1, the 0 to the 0. This 0, 1, 0, which has a code 0, 1, 1, propagates here. And this actually has to split. Every time we split, because when we were computing it, we were adding. So when we are going back, we are splitting. Every time we are splitting, we have to add 0 and 1. And so we keep going, and we get this result that says that the symbol 0, 1 is going to have a code 1. The symbol 0, 6 is going to have a code 0, 0, and so on. So this is the code. It's a variable length code. Not every symbol is represented by a code of the same length. It actually has a different length, and the length depends on the probability. The higher the probability, the shorter the code. And that's very easy to see because the low probabilities were added, and then when we are going back, we have to split. And remember, every time we split, we have to add a symbol, and we have to add a bit for that symbol. So basically the code becomes longer and longer. And we can actually go and compute, once again, the average length of this. So to repeat the process, we basically order the symbols according to their probability. That's what we did here. We start adding low probabilities. So we add these two, we got this, we reorder, and we keep going. It's a recursive process. So if you know how to go from one column to the next, you know how to go all the way. And then we come back. There is a couple of things that are very important to observe here. The code that you get in this way is what's called prefix free. And that's very, very important. Look at this column. When you see a 1, when the decoder sees a 1, it knows that it has to go here to A2. When it sees a 0, it basically says, okay, I have to wait for the next symbol. But there is no code here which is a full prefix of any other code. And that's very important. Otherwise, the decoder won't be able to reconstruct. Let's give an example of something which is not a prefix code. Let's say that the symbol A1 is represented by the code 1. The symbol A2 is represented by the code 0. And the symbol A3 is represented by the code 0, 1. Okay? So when the decoder sees 0, 1, basically there are two possibilities. It's either A3, let's say pixel value 100, or is A2 followed by A1, let's say pixel 0 and pixel 255. So there is a lot of ambiguity in the reconstruction. We don't know which one it is. And this is because this code is not what's called prefix free. This guy is a subset of this guy. That doesn't happen here. Let me just clear these annotations. None of these codes, so for example, the 00, you don't find it anywhere here. So when the decoder sees a 1, knows what to do. It puts the pixel value of A2. When it sees a 0, it says, oh, I have to wait because there are many codes that start with 0. If it sees a 0, another 0 next, say, oh, I'm done. I basically have 86. If, let's say, it's so the decoder receives a 0 and then a 1, says, oh, I have to wait because there are numerous codes that start with 0, 1. But then it receives another 1 and says, oh, I'm done. I don't have to keep waiting because there is nothing, there is no ambiguity here. And that's very important. And Huffman code, by construction, look how we basically split and split and split. And by construction, this is a prefix-free code. Now, how do we know that this is an optimal code? How do we know that with this set of probabilities, the process, the procedure I just explained, achieves the lowest possible the lowest possible length, the shortest possible length of a code on average. So that's a theorem we have to prove. We are not going to do that in this class, but that's a theorem that shows that Huffman coding basically achieves the shortest possible length. Now, you might wonder, what length can Huffman coding achieve, or any basically encoder of this style? So the basic idea is, if I give you a set of probabilities, how much can I compress? How much I go, and before I construct a Huffman code, I want to know, is it worth the effort of constructing the code? Will I compress a lot? And the way to do that is basically you compute what's called the entropy. And the entropy, which is written by H is entropy, is the sum over all the symbols with a minus here, I'm going to explain in a second, of the probability of every symbol log base 2 of the probability of every symbol. So you basically sum 0.4 times log base 2 of 0.4 plus 0.3 times log base 2 of 0.3 and so on. So this is actually at the end a positive number because all probabilities are below 1, and therefore the log of the probabilities are negative numbers, and then with the negative we get a positive. And Shannon's fair theorem basically says that we can achieve, basically asymptotically, we can achieve this code length on average. So this is basically what's achievable with this type of codes like Huffman code. We basically can compute this number and say, oh, that's going to be my average code length, my expected average code length. It's actually not so hard to understand where this formula comes from. We use a similar computation with the previous example. Here, the probability is basically the probability of the symbol appearing. And this is actually the length of the code that is going to be used for that symbol. So basically, what this is saying is that the expected length of that code is the log of the probability. And why it's only the expected is because you cannot have a code which is 3.2 long. You have to send entire bits. Either you send 3 bits or you send 4 bits. And that's why this is on average and the expectation, what you expect to be the code length. But this basically gives you an idea of what encoders like Huffman coding can achieve. So now that we know how to encode the bits that we are producing, we are ready to go into the next blocks of image compression.